guys, this is section 4.1, part 1. Today we're going to do mostly review of exponential functions that you've seen back in Algebra 1 and Algebra 2. All right, let's get started. So definition of our basic exponential function is f of x or y equals a to the x power. We have a couple conditions on a. A we call our base. It must be a positive number and it can't equal 1 to fit into our exponential function definition. It has a domain of all real numbers, meaning you can plug any number in for that power of x. The first few problems here are just some super quick evaluating problems, and we're going to review exponent rules as we plug numbers in here. You can use the calculator to help you if you need to. So in this first problem, we have f of x equals 2 to the x minus 5 power. All we're going to do is plug 4 into our exponent and simplify. So that gives me 2 to the negative 1 power. Remember, anytime you have a negative exponent, if we imagine this is a fraction, we can move that term to the denominator, and that makes our exponent positive. 2 to the first technically is there, and then we wouldn't simplify any further. 1/2 would be the final answer. If you type this in the calculator, it would tell you 0.5. Let's look at the next one. Negative 3 times 10 to the x power. If I evaluate for negative 2, that's negative 3 times 10 to the negative second. 10 to the negative second can be written as 1 over 10 squared to make that exponent positive. 10 squared, and that denominator is 100. And then if I multiply straight across, I'm going to have negative 3 over 100, or the decimal equivalent of that is negative 0.03. Let's say I have f of x equals 1/7 to the x power, and I'm evaluating for 1/3. So that would look like 1/7 to the 1/3 power. Another way to write this is the cube root of 1/7. That's what a 1/3 power is. 1/2 would be a square root, so on and so forth. And then this is something you would need to type in your calculator, either 1/7 to the 1/3 power or the cube root of 1/7, because we can't get any more exact than what it is right now. So we were looking for a approximate answer here. So let me type it in my calculator off to the side. So if I do the cube root of 1/7, I'm going to get approximately 0.52 if I round to 2 decimal places. And then finally, here we're going to evaluate 4 to the negative 3/2 power. I'm going to move it to the denominator first to make it a positive 3/2. That's the only thing that's changing when we use that exponent rule. And then anytime you have these rational exponents, you can rewrite them as, instead of 3 over 2, think of it as 3 times 1/2. So I can do 4 to the 3rd times 1/2, which this is the opposite of one of your power rules. It's called power to a power. If we wanted to simplify this, we would multiply the 3 and the 1/2 together, which would take me right back to that 3/2. You could also put the 1/2 in the parentheses and the 3 outside the parentheses, and that would be equivalent. To do this in my head, I would just do 4 to the 3rd, which gives me 64. And then 64 to the 1/2 power just means square root of 64, which gives you 8. If you did 4 to the 1/2 first, you would get 2. Take 2 to the 3rd, that would also give you 8. So you can see it doesn't matter which way I evaluate that. But again, if you have a calculator here, you can get these answers as well by just typing these in. So those should be quick little math Excel questions for you. Okay, the next couple problems are just some quick graphing problems. We're going to do these without the calculator. Because exponential functions are defined for all real numbers, you can plug any numbers in for x. I'm just going to use negative 2 to 2 in my table and plug them in by hand. If I do 2 to the negative second, that's the same as 1 over 2 squared, or just 1/4. 2 to the negative first is the same as 1 over 2 to the first, or just 1 over 2. Anything to the 0 power is 1. That's one of our old exponent properties. 2 to the first 2, and 2 squared 4. Again, if you have your calculator, you can use that to help you fill out this table. Let's plot our points. Negative 2, I'm at 1/4. Negative 1, I'm at 1/2. 0 at 1, 1 at 2, and 2 at 4. connecting my points, and we get, oh, that's a little crooked there. We get one of our parent functions, our exponential growth function, we call this. It's very important that you do not cross the x-axis. Remember, that was one of our properties of exponential functions when we talked about the parent functions, is that the x-axis was our asymptote, the line that our graph gets close to but doesn't touch. Okay, let's look at the next one. I'm going to use the same values here, -2 to 2 in my table. And I'll show you a couple of these. Let's say I'm going to do 2/3 to the -2nd. That's the same as 2 to the -2nd over 3 to the -2nd. That's an exponent rule, distributing that negative power to the numerator and denominator. Just review from Algebra 1. Because they're both negative, I can flip my fraction, and that makes the 3 squared positive and the 2 squared positive, which will simplify to 9/4. If I do 2/3 to the -1st, it's 2 to the -1st over 3 to the -1st. Or if I flip it, 3 to the 1st over 2 to the 1st, or 3 over 2. Anything to the 0 power is 1. 2/3 to the 1st is 2/3. 2/3 to the 2nd, we just square the numerator and denominator. We get 4/9. Let's graph those points. -2, I'm at 9/4, a little bit bigger than 2. -1, 3/2. 0, I'm at 1. 1, I'm at 2/3, and 2, I'm at 4/9. We're going to be, again, very careful here not to cross our x-axis. And we end up with what we're going to call an exponential decay function. So same properties here, only we are decreasing over all real numbers instead of increasing over all real numbers. A way to tell the difference in your original equation on if it's going to be growth or decay is your base number. If your a value is larger than 1, you're going to see growth. If your a value is between 0 and 1, it will be decay. Remember, part of the definition was that a must be positive and it can't equal 1. So this covers all of our bases with possible a values. If you want to check these graphs, you can type these equations in your calculator. Okay, so just listing some properties. A lot of these you saw with our parent functions before. We're going to edit our equation a little bit. This one's going to be a little more useful for us, so we're going to put a constant out front, and we're going to call that our a now times b to the x. If you guys did equations back in Algebra 1 and Algebra 2 with exponential functions, this is more than likely the basic function that you used. So we're going to say b is what we call the growth rate. So again, if b is bigger than 1, it's going to be growing from left to right. You can put your arrows there if you want. And if b is between 0 and 1, it's going to be decaying from left to right. Properties of these functions. Domain is all real numbers, forever left and right. Range, remember our asymptote, actually I'm going to do that first, is the x-axis. So our range is only positive numbers from 0, not including 0, to infinity. Intercepts, the only intercept you're going to have is you're going to have a y-intercept at the value of a. These functions are neither even nor odd. Remember, even means reflection over the y-axis and it will look the same. Odd means a rotation of 180 degrees or symmetry to the origin. And then finally, end behavior. These only have two ends, so it's sufficient to say x approaches negative infinity, x approaches positive infinity, and then what y is approaching. On the left, y is approaching the asymptote, 0, and on the right, y is approaching positive infinity. Now, if we look at the exponential decay functions, a lot of these properties are the same. Domain is the same, range is the same, asymptotes are the same, intercepts are the same. It is a neither function as well. And then the end behavior is going to change slightly now because, again, it's decreasing versus increasing. On the left side of this graph, my y is approaching positive infinity. And on the right side of this graph, my y is approaching 0. Okay, so let's solve some equations trying to find the function here. So here they're using a c and an a instead of an a and a b. You're going to see a lot of different variables. They kind of interchange here, but it's the same form. And anytime you're finding an equation, you're trying to find values for everything except for your x and y. So here we're trying to solve for c and a. I know that I have 2 points that go through my function. Now this is not a linear function, so we're not going to do anything with slope. All we can do is plug in these values and see what happens. So I'm going to start with 1, 1. 1 goes in for y, and 1 goes in for x. So I have 1 equals c times a. When I do a to the first, I get a. And that's really all we can do with that first function. In the second function, I'm going to plug in 1/5 for y and 2 for x. So what we've created here and here is a system of equations, 2 equations that contain the same 2 variables. So we're going to put these together. Typically, you could use substitution or elimination. Substitution is going to be easier here because we don't have linear terms. So I'm going to get, let's say, it doesn't matter really, the c or the a. Let's say I get the a alone in this equation on the top. So that would be a is equal to 1 over c if I divide both sides by c. Now I can take that 1 over c and plug it in for a in the other equation. So that would look like 1/5 c times 1 over c, 1/5 equals, forgot my equals. 1 over c replaces the a, and we square it. Okay, so now let's simplify that. I have c times, if I square the numerator, it's 1. If I square the denominator, it's c squared. If I multiply c over c squared, think of it like a c over 1. I'm going to have 1c cancel. So it's going to leave me with 1 over 5 equals, if 1c cancels, I have a 1 on top and a c on the bottom. And then if you don't see it yet, you can always cross multiply, but you're going to get c is 5. Once you know the first variable, you can plug it back in anywhere. Like here would be a good location to plug it back in. 1 over 5 equals a, and there's our value for a. So our final function is f of x equals c, which was 5, times 1/5, which was our a, to the x power. And we cannot simplify any more than this because that 1/5 is to the x power. The 5 and 1/5 cannot be multiplied together. Okay, let's try another one. Here we have a slightly altered version of our function. Instead of a number being multiplied out front, it's added on. So there's been a vertical shift up or down, if we want to think about it as if we're doing our transformations that we've talked about before. So again, I have 2 points to plug in. I'm going to start with 0, 3 because it's just some nicer numbers. So my y is 3, a to the 0 plus b. And anything to the 0 power, remember, is 1. So actually, we can solve for b now. If I subtract 1, I get b is 2. So now, if I go back to this original function, I don't need a system of equations. I can say f of x equals a to the x plus 2. I know what b is. So now we're going to plug -2 and 6 in and see if we can solve for a. So 6 is my y. A I don't know. X is -2 plus 2. Okay, and a is the only variable, so let's solve for that. I'm going to subtract 2. And actually, let's do that in the next step. Instead of an a to the -2nd, I'm going to write it as 1 over a squared. Remember, we can move it to the denominator to make it positive. I'm going to multiply both sides by a squared. So over here I'll have a 4a squared, and on the right I'll just have a 1. Divide by 4. And then take the square root of both sides. So a equals, technically, if I take the square root of the numerator and denominator, I'm going to get 1 over 2, and I should put a plus or minus in front of it, but remember that a is a base to an exponent, so it cannot be a negative number, so we're only going to include the positive value. So my final function, if I fill everything in, is 1/2 to the x power plus 2. Now this problem also wants us to compute f of 4. So once we have our function, we can do that. f of 4 equals 1/2 to the 4th power plus 2. So 1/2 to the 4th, that's 1 to the 4th, or 1. 2 to the 4th is 16 plus 2. Think of 2 as 32/16 if I get a common denominator, so our final answer is 33/16. Okay, in the next problem we're going to graph a more complicated function, but we're going to still do it using the same method. We're going to use our XY table. And again, your domain is all real numbers, so you can plug in anything you want here. I'm going to start with -2 to 2. And I'm hoping to see where my y's get close to a specific number because that's going to reveal my asymptote to me. Your asymptote could change based on what transformations have happened to this function. If you don't feel like -2 to 2 kind of reveals the asymptote, then instead you can just plug in some other numbers, something higher than 2 potentially, or lower than -2. You can use your calculator to help you here, or even a basic calculator would be fine. For example, if I plug in -2, that would be 2 times 3 to the -2 plus 1 minus 1. So that would be 2 times -2 plus 1 would give me -1. 3 to the negative first is 1/3. 2 times a third is 2/3 minus 1 gives me -1/3. And then we can repeat the process. Let's plug in -1. So we have 2 times 3 to the -1 plus 1 minus 1. Well, 3 to the -1 plus 1 is 3 to the 0 power, which is 1. 2 times 1 gives me 2, minus 1 gives me 0. Let's say I plug in 0. Do that up here. 2, oop, I wanted a different color. Try that again. There we go. 2 times 3 to the 0 plus 1 minus 1. That would be 3 to the first times 2, which is 6, minus 1, which gives me 5. Let's say I plug in 1. 2 times 3 to the 1 plus 1 power minus 1. That's 3 squared, which is 9, times 2 is 18, minus 1, which is 17. So these are getting pretty big. I'm actually not going to plug in 2. I'm going to plug in -3 instead, because I'm trying to get to a point where those y's are going to get a little closer together and reveal my asymptote. So let's see, 2 times 3 to the -3 plus 1 power minus 1. So that would be 3 to the -2nd, which is 1/9. 2 times 1/9 is 2/9, minus 1 gives me -7/9. And you can see these numbers are getting smaller and smaller. They're getting closer to -1. If you're not sure, though, you could plug in -4, -5, and make a larger table. Let's plot our points. -3, -7/9, -2, -1/3, -1, I'm at 0, 0, I'm at 5, and 1, I'm at 17. And there is my function. Now, if you wanted to name some properties here, you could name the domain. And domain you can name at the start, because remember, domain of these is always all real numbers. Next, I would name my asymptote, which is the line that your graph is getting close to but not touching. You can see that we are approaching -1, and you can see that in the table as well. We're getting closer and closer to -1 on those y values. Don't forget a y equals in front of these because they are a horizontal asymptote. And then once you know that, you can say your range is, in this case, -1 with a parentheses all the way to infinity. Now you may have a Math Excel question that asks you to name the transformations that have occurred. So let's say we started with this basic function, y equals 3 to the x, and then we graphed g. We want to name what the 2, the +1, and the -1 do. So this will go way back to a couple chapters ago with that chart A, B, C, D. This was in section 2.7 if you need to look back at your notes. The number out front performs a vertical stretch or shrink. In this case, it is a vertical stretch by 2 because it's a number larger than 1. When you have exponential functions, anything that's in the exponent is considered inside the function. So that +1 up there, that's like our C value. That moves our graph left 1 unit. And then the -1 at the end, that's that D value, it moves it down 1. So if you saw that you know that graph's going to move down 1, then that can help you with that asymptote if you're not sure as well. Remember, our original asymptote is on the x-axis. If I shift the graph down a unit, that means our asymptote's also going down a unit, and that's why we're seeing that asymptote at -1. Okay, so this is just the opposite of the previous question. Here you are writing an equation. You're given a basic function to start, one of our exponential functions. You'll always be given a number for the base. They're not going to use an a. They'll use some number that's larger than 0. And they're going to give you the transformations. You're just going to fill them in. So I'll do this like we did it before. I'm just going to kind of make some space here and fill in things as I need to. So 2 to the left, that would be a -2 inside the function. So that would be up in the exponent. 5 up would be a +5 at the end of the function. And then some people like to put that base in parentheses, so you can do that. Let's call that optional. Okay, in the next problem, we have y equals 3 to the x power. Here, I want to take this and I want to shift it 3 to the right. So 3 to the right. Oh, I made a mistake earlier. I was going to say that was a -3. That should be a +2 up there. Sorry about that, guys. Hope I didn't make that mistake in the last problem. Oh no, we're good. We're okay. Whew. Sorry I missed that. Hopefully you guys caught me. And then it's reflected over the y-axis. A reflection over the y-axis, review from before, was a negative inside our function. So we want to put that negative in front of the x, but remember it needs factored away from the x, so you want to include a parentheses there as well. You could also distribute the negative in if you want to. And you could also put a parentheses here if you want to. Let's call that optional. Okay, last one of these. Here I have y equals 1/2 to the x power. We want to stretch vertically by a factor of 2, so that's a number out front of my function multiplied. If it's stretched, it's bigger than 1. If it's shrunk, it's smaller than 1, so I'm just going to put a 2 out front there. And then I want to move it 5 units down, so just a -5 at the end. And if you wanted to check these, you could plug them in your calculator and see if those transformations have occurred, or in Desmos too. That's a great place to try it. Okay, that's going to be the end of section 4.1, part 1. I did put on this last slide here the rules for exponents as far as like when you add powers, subtract powers, distribute powers in. There's our 0 property and our negative exponent property that I've referred to in this lesson. So if you feel like you need to write these down in your notes just for reference, go ahead and do that. If not, that's fine as well. And then tomorrow we'll start talking about 4.1 big ideas. Thanks, guys.